Alright guys, let's go ahead and get started. First thing, as always, can I get a sound check? Just make sure you guys can hear me. Nice, thanks guys. Alright, well, welcome to Monday. I hope you guys had a good weekend. And we are in the final full week of the course, and this is the penultimate lecture of the entire course. We got this one, then Wednesday, and then after that, the only thing we have left are tests and reviews for test. So, of course, you guys got some projects to work on and some assignments to do. So, before we kick things off, are there any questions, comments, or concerns? I know you got a couple things due tonight. I think you got a project and assignment number 11, I believe. Let me take a look real fast.
It is 11.
Yeah, assignment 11 is due today, as well as project number 2 are both due today. Are there any questions about those two assignments? And of course, you just got your last project. That'll be due December 2nd, which is the last day of class. I see some folks typing. I'll wait and see what they got to say. For assignment 11, Michael asks, if it doesn't say anything about propagation delay, should we assume there isn't one? Right. If it doesn't say anything, don't worry about it. Okay, Luke asks, is it the same rules as the last project, correct? Meaning if it passes the test benches completely, it means you got 100. Yep. The test bench says you're good, then you're good to go. Yeah, there's no bonus points for doing it the hard way. All right, if there are no more questions, let's go ahead and do today's lecture. Today's going to be pretty relaxed, I think. We're going to look at doing what they call signal tracing, and we're going to take a look at some timing charts. Basically, what we're going to do is we're going to sit down and look at two types of sequential circuit and just kind of work our way through their behavior. So, looks like we have one more question there. Two more questions. Let's see. Wally, didn't you finish the last project that still works? Does that mean there? So that's I don't know. I didn't do dollar finish on the last project that still worked. Does that mean that there's a way I can solve the project without doing this? I mean, you need to have, you ought to have the finish as a just matter of course. Although actually, you shouldn't have. You should just be using the test bench that you were given, so that shouldn't make a difference at all. Yeah, I don't know why your computer froze while it was running the output there. So, and then Adrian asks, maybe we can take a look at it during office hours. Adrian asks, the PowerPoint slide will be available after lecture. Yep, you bet, with the squiggles and all my notes and stuff on it as well. So, all right, let's go ahead and dig into this lecture. So just a quick overview. We're going to go through our procedure for analysis. We'll talk about our two different types of sequential circuits, Moore and Mealy, and what those are, and then we'll work through just two examples. This will be a pretty easy lecture. I think we'll get out a few minutes early as well. Oh, there you go. Wally figured it out, man. You got to have that always at pause edge line. Okay, let's talk about the analysis procedure. So when we're taking a look and we're doing an analysis of a sequential circuit, here are kind of the steps that we want to do. The first thing we want to do is assume an initial state of the flip-flops, right? You got to set everything to some known state. Unless otherwise specified, you should always just set your known state to 0, right? All zeros is the right place to start. By convention, that's where you're going to start all of the time. And when we go to reset, that'll drive our flip-flops to 0. So always just set all the flip-flops to 0, again, unless you're told to do otherwise. Step 2, for the first input in a given sequence, determine the circuit's outputs and the flip-flop inputs. Basically, just do the sort of, input equations for the flip-flops and figure out what those inputs are going to be for the first input in a sequence. Step 3, then figure out what the next state is going to be, what the output state of the flip-flops is going to be on the next active clock edge, either rising edge or falling edge. And then 4, determine the outputs that correspond to the new states, what are the outputs of the circuit. And then finally, step 5 here is just repeats steps 2, 3, and 4 for each input in the given sequence, right? So if you've got a sequence that's 5 bits long, you're just going to sort of go through each of those 5 and see what those signals are going to be. So it's a pretty simple sequence. We're just going to take our time and sort of work through them. Are there any questions about this procedure? All right, in that case, let's take a look at our types of clocked sequential circuits. There are a bunch of different types of sequential circuits, but primarily they all kind of fall into these 2 categories, named for the computer engineers that developed them. First one is Moore. A Moore circuit is a circuit in which the output depends only on the present state of the flip-flops, right? So there is no input to a Moore circuit. A Moore circuit is sort of self-contained. It has an initial state, and it just triggers through and produces outputs. There's no inputs to a Moore circuit. Or at least the output depends only on the present state. There might be some input to the flip-flops, but the output is only dependent on the present state of the flip-flops. And then a Mealy circuit is the output depends on the present state of the flip-flops and the circuit input. So you can feed the inputs around the flip-flops to the output and have that affect the output of the circuit. So a Moore circuit is output is just tied to the flip-flops, and a Mealy circuit, the output is tied to the flip-flops and the inputs of our sequential circuit. So let's take a look at an example of a Moore sequential circuit. So here's what we're going to do. Let's unpack some stuff. First off, we see that it's a Moore sequential circuit because notice that Z is only dependent on the flip-flop. So here we've got that Z is equal to A XOR B, right? It's tying from A, it's tying from B, so it's not dependent at all on the input X. The next thing is that we've got an input sequence X is 0, 1, 1, 0, 1. So we're going to use that to sort of clock through our signal. And also we notice that it's a rising edge since there are no inverters, no inverting bubbles. That means we've got a rising active edge for our clock. So now what we need to do is go through that process and just unpack this circuit a little bit. So what was our 0, 1, 1, 0, 1? I'm going to write that over here. X equals 0, 1, 1, 0, 1. So remember, the first thing we do is we set everything to our initial state. So let's just go ahead and say that, well, really, we just have X, and then we have A. Make sure I don't write over myself. A and B, and ooh, let me move that around a little bit. So X equals 0, 1, 1, 0, 1, and then I'd be down here for what our X is going to be, what our A is going to be, what our B is going to be, and then what our Z will be. So the first thing we do is we initialize everything to 0. So we won't even consider what our input X is. We'll say that A and B is 0. And then if A and B is 0, remember that Z is equal to A XOR B. Well, then Z is going to be equal to 0. So next up, we've got what? X is equal to 0. So we've got a 0 here. And let's see, a 0 on that XOR gate. Now we've got to sort of come around. We know that our initial state was A is equal to 0, so we've got 0 or 0 on this case, in which case B is going to be 0. And then here on this side, we've got B XOR B prime. B prime is going to be 1. So that means DA is going to be 1. So that means that we've got our next circuit, or excuse me, our next values are going to be what? 1, 0, and that means Z is going to be equal to 1. Are there any questions about how we did all that? And now we just sort of chunk through the circuit. Let me go ahead and erase these guys, and let's do the next one. Okay, so Michael asks, or says rather, I don't think I really understand how to find the next state. So there's two parts to the answer to that question. The first one is it depends on the flip-flops. And in this example, so a flip-flop's next state is going to sort of hinge a little bit on what type of flip-flop it is. But here we've got D flip-flops, which are transparent flip-flops, which means that they're just 1 to 1, right? So A plus is equal to DA. And B plus is equal to DB. Well, that means that whatever signal goes here on the input of our circuit, on the next active edge, that's what's going to be our next state, right? So here we had all 0, so we had 0 or 0, gave us a 0 on DB, meaning that our B plus, actually I should probably make these pluses, A plus, B plus, are going to be, for B is going to be 0, right? But here we had X and B prime, so that's 0 and B prime is 1, since B was 0, means we have a 1 at DA, which means that we got a 1 for A plus. Did that answer your question, Michael? So basically you just solve the logic for whatever is attached to DA, and that's what gets passed. For a D flip-flop is what gets passed straight through. All right, so let's take a look at the next one. Erase real fast. Erase. All right, so the next bit in the circuit is the 1. So we're going to have a 1 here, which means that we'll have a 1 on both of those inputs. And then let's see, our initial state A was equal to 1, so that means it's a 1 here. B was still equal to 0, which means that we had a 1 here. So now on the right-hand side, for B, we had 1 or 1 is going to give us 1. So we're going to have a 1 at B plus. And on the left-hand side here, we've got 1 XOR 1, means we're going to have a 0 at DA, which means we're going to have a 0 at A. And then because Z is XOR A and B, means we're going to have a 1 on Z. And then we move on to the next one. So that's going to be a 1 again. Let me reset a little bit here. Get my eraser going. Erase that. So now we're going to look at this third bit in the sequence, 1. In fact, let me just do this. I'm going to go 1, 0, 1 to complete the sequence. So now we're on this next line. So let's see, X is 1, so that's going to be 1s on both of these guys. Cody very formally asked, sir, are we using the next state values of A and B to determine Z? Shouldn't we use the present state values instead? So Cody, how would that change things? Or I guess another way to answer that question would be, right, so like, I mean, you can think of these guys as B plus, right? And we're talking about the next step of the sequence. So we're saying on the next clock cycle, these are what they're going to change to, and then Z is going to be the output of that. So we're looking ahead to the next one, if that makes sense. In this instance, yeah, because we're saying on the next cycle, if x is equal to this, well, what is that going to do to the next ones? And since z is, I mean, I know it gets a little abstract, right? Because we're sort of being fast and loose with what is present state and what is next state. But you could also sort of say that z is equal to the next state in this case. Maybe a better way to write it would be to say, like, well, this is z plus. That's the next one. Since we're talking about what happens next. That's a good question, though. Okay, so now let's say we're looking at this row. We had 1 and 1, so 1's on our x's. B was equal to, A was equal to 0, so it means we had a 0 on A. B was equal to 1, which means we had a 0 here, which means now we're going to have a 1 on A for the XOR gate and a 1 on B. So we're going to go here, 1, B is 1, which means Z is going to go to 0. And we go on to the next one. So we erase, 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 erase. Get the pin back. All right, so now in the next one, we have x's are zeros now. 0 and 0. A and B were both 1, so that's 0 and 1. And B is 0, so, A is 1, or B is 1. So B prime is 0. So it means we're going to have a 0 on A and a 1 on B. So we're going to have 0 and 1, which means that Z is going to be 1. And then finally, the last one is 1. So let me grab my eraser. All right, so finally we've got x is equal to 1, so we got 1 and 1 on our input gates, and then A was equal to 0, so we have 0. B was equal to 1, so we have B prime is equal to 0, so we've got 1 and on A, and then 0 or 1 is 1 on B, so that's going to be 1 and 1, which means a 0 on Z. So there we go. So this type of analysis is called signal tracing, and it sort of makes sense because that's literally what we're doing, right? We're sort of saying, all right, X is this, and we're sort of tracing the signals as they go through our circuit to get an idea of the behavior of the circuit. Are there any questions about this analysis? It's really the crux of what we need to do today. All right. So if we kind of move on from all of this, right, we're going to see, hold on, let me do things fast. Yeah. We could also have done it as a timing diagram, right? If we had them sort of laid out next to each other. It's kind of hard to do that here on the PowerPoint, but, you know, let's see what we had. So if we look at every clock cycle on the rising edges, let's see, we have 0, 1, 1, and I'm just tracing up from the rising edges of the clock, right? So that's a 0, and that means that's going to be a, not a 0, 1, right on. And remember what we had. A was X or B prime, B was equal, rather dA, dB was equal to, what was it, X or A, and Z, of course, was equal to A XOR B. So you can kind of see that going on here, right? So let's see. If B is at 0 and X was at 0, then here A went, let's see, hold on, I'm getting a little turned around. A was equal to, yeah, 0 here, a 0 here, dA was equal to X or B prime, gets us a 1 there. And then if we look at B, B is X or A, X is 0, A is 0, means B stays at 0, right? And then we can sort of trace the same process through here, right, using the timing diagram. And we can do that for each step here in the beginning. So, any questions about this timing diagram? Or does anyone want to see us do a few more steps? All right, let's just go ahead and work through it then. We'll see some more steps. All right, so we go to the next one, right? So on the next one, x is 1, a is 1, b is 0. So then we look on the other side here. So if a is x or b1, yeah, the values change just on the rising edge. So then that means it's going to be, 1 from x, and let's see, b was equal to 0, so b prime was equal to 1. So b was equal to 0, so b prime is equal to 1. X XOR b prime is equal to 0. I mean, it's really hard to do the tracing. That's why it's a lot easier just to look at the diagram or the logic diagram and sort of trace signals directly. Going through and doing the math with the timing diagram is pretty tricky. So let's look here at Z. I'll just do this last one and then we'll move on because it's getting kind of weird and I don't want to confuse everybody even more. I won't ask you to do it on a timing diagram. But let's say here at the rising edge, Z, which is equal to A XOR B, we got A is 1, we got B is 0, means that Z stays at 1. So basically we can trace through here and see that it sort of makes sense. Let's do one more. Here we go. So on this rising edge, we've got, so for A should be X or B. So if X is 1 and B is 1, B prime is 0. So 1 XOR 0, excuse me, 1 XOR 1, no, 1 XOR 0, I'm confusing myself, is equal to 1. Z is equal to A XOR B. We had 1 and 0. Oh, this is kind of interesting. Hold on. So what's going on right here? So Z is equal to A XOR B. Then how is it going to? Oh, because I'm dumb. Because it's 1. It's A XOR B. No. That should be equal to 1. But why?
Isn't it because when both of them are 1, then Z must be 0 because it's
yeah, except now I'm thinking there's an error in this diagram from the book, right? But they're not both 1. You're absolutely right? So B is equal to 1, but A here is equal to 0. But here we see it drop to 0. Why is that? Oh, you know why it is? Because I'm dumb. It's because the transition happens after the fact. This is exactly what we talked about, Cody, right? We talked about the difference between where we were looking at it, like is it on the next state or the state that you were coming from? And here, it's because we're looking up here, right? At 1 and 1, and because Z is dependent on that, that's why it goes to 0. Cool, all right, so I'm glad we did these extra steps. So this illustrates the fact that Z is not dependent on the previous state, but is in fact dependent on what happens next. Yeah, I was confusing myself, man. All right, but that's pretty cool. I'm glad that kind of illustrates that. So we'll go ahead and leave it there now that everyone is good and confused. Are there any other questions about this diagram? All right, and here on the next slide we can see essentially the chart that we drilled out before. Or see where we start everything at 0, and then we work our way through the sequence. And then if you go back, we got 1 1 0 1 0 on our output here, which is what we got there. And then here B was 0 1 1 1 1, and B is 0 1 1 1 1. And A is 1 0 1 0 1 1 0 1 0 1. So just a little bit of a double check to show us our results there. All right, that was the more example. Any other questions about this example before we move on to the next example? What do you mean the table doesn't line up with the one we just made? Oh, it is. You're right. They've got it offset by 1. Why? Why did they do that? So we had 0, 1, 1, 0, 1. Oh, I see why. Because they were doing the inputs offset, whereas we were drawing them off. So to address Cody's question there, no, it's not a big deal. It's just that we were drawing them kind of in a line and saying, well, that's going to drive us to the next states. Here they were saying, let's draw it offset, and having what the next state be driven be like lagging behind 1. So it's all there. The notation they used in the book is just a little bit different than ours. Does everyone see what we're talking about? Right here, they've started their sequence at the beginning in their table here, whereas we started ours on the first row. So, but that shouldn't make a difference. All right, let's move on to the Mealy circuit. All right, so remember Mealy circuit is where, so Moore circuit was the output is dependent just on the flip-flops, and a Mealy circuit is the output is dependent upon the flip-flops and the inputs. Sorry, getting a little distracted. Okay, so let's go ahead and do the same thing. X equals 1, 0, 1, 0, 1. So here stuff is a little bit different, right? Let me write our 1, 0, 1, 0, 1. Because we've got what kind of flip-flops here? So we've got, yeah, so Adrian and Cody, you're both correct, right? So yeah, so we've got a bubble here. So these are falling edge flip-flops, but also they're JK flip-flops, which means that we need to have an equation that kind of defines both of them. And in fact, let me go and grab, I'm going to break out of the PowerPoint real fast because there's one other diagram I want to add here kind of on the fly. I need the textbook. There we go. Okay, so let me jot this down. For a JK flip-flop, we're going to have Q plus is equal to, so actually, let me roll that back. Remember, for a D flip-flop, Q plus was just equal to D, right? But for a JK flip-flop, it's a little bit different, right? Q plus is equal to J and Q prime, or K prime and Q. So we're going to need this for the next part. Okay. Any questions about what I've just jotted down right here, what this is? So this basically just means that A plus will equal JA and A, or KA prime and Q. Well, the midterm is going to be multiple choice, Ian, so I'm not really sure how you're going to derive equations on a multiple choice exam. You will need to know what they are, though. You'll need to know that this is the equation for a JK flip-flop, and, you know, pick it up on a multiple choice question. But no, you're not going to like derive them by hand or anything like that. All right. So let's, while Adrian's typing his question here, let's go ahead and set up our table that we need to do, right? So we're going to have X, we're going to have A, we're going to have B, and we're going to have Z, right? So I'm going to sort of write them as the pluses on the sides. And then so we're going to initialize everything to 0. So that means 0, 0, which means that what is B, hold on. Adrian asks, so we should be able to recognize the next state equations? Yeah, you should be able to recognize them. So if I say, you know, which of the following answer choices is the next state equation for a JK flip-flop, you should be able to pick up that one. Okay, so let's do this real fast, just to kind of keep everything a little bit better organized. So we are going to do the offset thing now. So we're going to say we initialize X. I'm going to put it in parentheses here just to say X was started at 0, and A and B are both 0. So what is Z? The exam is 1 week from today. Michael. Okay, so what is Z going to be in this case? So if X is 0, well, we're going to have 0, 0 right off the bat, so we know we're going to get 0, 0 there. That's going to be a 1. A prime is going to be a 1. B is going to be a 0, which is going to give us a 0 there, which is going to give us a 0 Z. So we initialize everything with all zeros. Good job, Cody. And now we go through and do the stuff. Let's see. All right, so right off the bat, our first one is 1. So let's go ahead and figure out what our inputs here are. So Ka is going to be equal to 1, as is, here, I want to erase this, it's going to confuse me. Let's get rid of those, because we're not really interested in the whether it's rising or falling. So Ka is going to be equal to 1. JB is going to be equal to 1. KB is going to be equal to X and A, which is 1 and 0, which means it's going to be 0. And X and B is going to be 1 and 0, which means it's going to be equal to 0. So let's say we'll use the bottom, some space down here. Hold on. 1, 0, 1, 0, 1. All right, we'll say that A prime is going to be equal to, we've got it up here. I just chopped a huge line through it. Is going to be equal to what? JA is 0, and A is 0, or KA prime is, if KA is 0, KA prime is also going to be 0, and I need to make a slight tweak to that. That shouldn't be Q, that should be A. And that should be A prime. So let's roll that back just a little bit. All right. So let's see, what was J? J was 0. A prime, so if A is 0, A prime is 1, still going to be 0. Or, let's see, Ka prime, if K is 1, K prime is 0, and A is equal to 0, which means that we have 0 or 0, and A is equal to 0. Now B prime, B plus should be equal to JB and B prime, or KB prime and B. So B prime is going to be equal to, let's see, JB is 1, and B prime, B is 0, means B prime is 1. Means it doesn't matter what this is, because it's going to be 1. So there we go. That's B plus. Now let's do Z. So let's see. Our x's was 1. So 1, 1, 0. A is 0. So that's going to be 0, 1. And B is 1, meaning B prime is 0. So I think we've got zeros in every AND gate here. So that's going to be 0, 0, 0, meaning that Z is equal to 0. All right. That was a lot to unpack. So are there any questions about any step of that process? Or did I make a mistake even? All right, in that case, let's go ahead and reset and let's do the next one. Oh, wasn't done. Erase, 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 erase. All right, so let's do the next one. So in this case, x is equal to 0, so JB will be 0, KA will be 0, we got a 0 here, a 0 here, a 0 on x, 0 on x, a 1 on x prime. So now let's figure out what A is. JA is equal to, well, we've got x and B here. B is equal to 1, still 0 there, so it doesn't really matter. 0. A is 0. That's going to give us a 0 there. So JA is equal to 0. A prime, if A is 0 up here, then A is equal to 1. Not that it matters because it was still equal to 0. And then, let's see, or KA prime. KA was equal to 0. So K prime is equal to 1. And A is equal to 0. So now that gets us 0 or 0, which gets us 0. And then B plus is JB is equal to 0. B prime is also going to be equal to 0, since B was equal to 1. Or KB prime, so KB was 0, so KB prime is 1. And B was equal to 0. Oh, excuse me, no, B was equal to 1. So that's 1 and 1. So that equals 1. All right. So let me go back and fill in. A is up here. So if A was equal to 0, that means we had a 0 there. And a 1. Ethan says, sorry, I missed this. We have to give an initial value to A, B, and Z at the start of the figure, at the start of this to figure the rest of it out. Yeah, you got to start from someplace. Figuring out the initial value of Z is like not that important, but you've got to have initial values for A and B in order to figure else everything out, right? Because our next state equations are dependent on what A and B were. Okay, so let's see. Now, let's see, B was equal to 1, so B prime here was equal to 0, and B was equal to 1. That means we get a 0 here, 0 on the second AND gate, and a 1 on the first one, which means now we got a Z equal to 1. All right, now let's do the next one. Michael asks, will the next state equation always be the same? I'm assuming you're referring to, let's see, like this equation and by extension these equations, Michael? Yeah, so those will always be the same, and those are just dependent on whatever flip-flop you're using. The only thing that changes is what our flip-flop inputs are, or excuse me, like what JA and what KA are, and what JB and KB are, and that's going to depend on this circuitry here. All right, let's do our next one. Okay, so x is equal to 1, so let's go ahead and just populate our 1s everywhere. We got x equals 1, x is 1, x prime is 0, means ka is 1, means we got a 1 here, we got a 1 there, and we got a 1 there. A, when the previous a was equal to 0, so that means we're going to have a 0 there, a 0 there, and a 1 there. And b was 1, so that means, I didn't mean to populate those guys yet. Stop. I want to do those next. Okay. All right. So now let's go ahead and do these guys. So we had a 0 here, we had a 1 here, which means that we're going to have a 1 on JA and a 0 on KB. So looking at A plus, JA was equal to 1. A prime, A was equal to 0, so A prime was equal to 1. Well, that means that A is going to equal 1. Now we're looking at B plus. We've got, what, JB is equal to 1. B prime, B was equal to 1, so that means B prime is equal to 0. So we got to look at the next one. Or KB prime, KB was equal to 0, so KB prime is equal to 1. And B was equal to 1, so 1, 1. Gives us a 1, so we got 1s here. And then we've got A. So Z is equal to, so B, both A and B are equal to 1, so B prime is 0. A is 1, 0, and 1 means that we've got a 0 and a 1 and a 0, which means that we're going to get a 1 on Z. And we erase and restart. Signal tracing is an extremely tedious process. All right, let's do the next one. X is 0. So we got 0, 0, 0, 0, 0, 0, 1. All right, then looking down here, we got A is equal to 1, so we're going to have a 1 there. And B was equal to 1, so we're going to have a 1 there. Now we calculate A plus. I bet you it's going to be a lot of zeros, right? So that's going to give us a 0 at KB and a 0 at JA. So JA is equal to 0. And A prime is also equal to 0. Or KA prime, KA is equal to 0, so KA prime is equal to 1. And A is 1. Means we got 1 for A plus. And then B plus, JB is equal to 0. B prime is equal to 0. Or KB prime is going to be 1, and B is equal to 1. So they're both going to be 1 again. So that's a 1 and a 1, and next is 0. So that's going to be 0, 1, 0, and 0 and 1 means we're going to have zeros, zeros, zeros. Means our Z is going to be equal to 0. And the last one. All right, so now, last one, X is equal to 1, so we've got a 1 on JB, we got a 1 there, we got a 1 there, we got a 1 there, we got a 1, a 1, and a 0, and then we had A and B are 1, so that's going to be 1 and 1, meaning we have a 1 on JA and a 1 on KB, so you're looking at A plus, JA is equal to 1, and A prime is going to be equal to 0, or KA prime is going to be equal to 0, which it doesn't really matter, but A is going to be equal to 1, which means that A prime is going to be, A plus is going to be equal to 0, excuse me, equal to 1. Now we're looking at B plus. JB is equal to 1. B prime is equal to 0. Oh, wait, hold on. How did I do that? It must be a Monday morning, man. 0 and 0. Because Boolean algebra is a thing. 0 and 0. All right. Now, next up on B plus. KB prime is going to be 0. Meaning it doesn't matter. The next one is going to be 1. It's going to be 0. So we're going to have 0, 0. So that's going to be a 1. That's going to be a 0. That's going to be a 1. That's going to be a 0. Meaning we have a 1 and a 0 and a 0. Meaning that we get a 1 for Z. And there's that. So there we go. Signal tracing for our Mealy sequential circuit. So the biggest take homes here, the things I need you to know for the exam or care about you knowing for the exam are really just, you know, what is the equation for each of the flip-flops. So if I say, oh, a T flip-flop or a D flip-flop or whatever, right, those are the equations. And then if I give you sort of a set of initial conditions, can you give me the next set? Cody Baker says, wait, what? Sorry, Cody, that question's a little vague. Could you be more specific? Oh, yeah, no. That was a wait, what moment. It should definitely be 0, not 1. Still drinking the coffee. Okay. So that is, we're going to leave it right there for today. Are there any questions about that? Like I said, the biggest take home is, can you sort of set up what the circuit looks like and tell us what's going to happen on the next state? And then do you know those characteristic equations for our flip-flops? So any other questions, comments, or concerns? All right, in that case, don't forget, assignment 11 is due tonight. Project number 2 is due tonight. Project number 3 is on the table and is due in a couple weeks. And we only have, and then the third midterm will be 1 week from today, and we'll do a review for that on Friday. Ethan asks, one quick question on the project. Should we name it Project 2.v or our name like the last one? You should name it. Actually, you know what, Ethan, I'm glad you said that. I'm going to send that out in an email. But go ahead and name it Project 2. The reality is it doesn't really matter, but if you do, well, it was also Project 1 on the last test bench, and I asked you to change it. But Max said it doesn't matter, and actually if you leave it as Project 2.v, it actually makes his life a lot easier. So then he doesn't have to check anything. So go ahead and just leave it Project 2.v. Awesome. All right, thanks guys. I'll see you on Wednesday.